Hi everyone, I'm KAVIVARTHAN MANNIVANAN, a data engineering student from section 03, first semester, first year. In this video, we will be presenting our digital logic project regarding network packet transmission monitoring system. We, from Group 6, consisting of 4 members, which is myself, Kavivarthan Analalaki Manivanan, A24CS0093, Muhammad Hafiz bin REEPEI, A24CS0133, Muhammad Adam Ashraf bin ZAMRI, A24CS0119, and Joshua Ling Shang Yang, A24CS0089. So, as I mentioned earlier, we are from Section 03, Group 6, consisting of 4 members. First of all, we would like to thank Dr. Farkhana, our digital logic lecturer, for providing this opportunity to involve ourselves in completing this project. Her guidance and knowledge throughout this semester really helped us in completing this project. Besides, we would also like to thank Dr. Muhammad Fuad Rohani for preparing and coming up with this incredible project, which is regarding the network packet transmission monitoring system. By involving ourselves in completing this project, we are able to understand how the combinational logic circuits, memories, and functions are linked and used in real life by creating the transmission monitoring system using the circuit. Finally, we would also like to thank our fellow classmates and course seniors for their guidance, which played a crucial part in completing this project. Now, let's take a look in the background of the project. In this project, we aim to implement a network packet transmission monitoring system which is created using this circuit and will be explained later. A packet data from source computer from one lab is being transferred to a destination computer in another lab via a single cable line. We have achieved this by using multiplexers in our DEET circuit, which also will be explained later. The user, on the other hand, is able to define a maximum number of packet data transmitted, and they are also able to define a 4-bit password for security purposes. So, in general, combinational circuit components used in our circuit includes LEDs, switches, basic gates, comparators, decoder, multiplexer, and a 7-segment display. While sequential circuit components used include clock enabler and D flip-flops. For advanced feature, we have included a 4-digit password system which incorporates decoders.
And now I will talk about the problem part. The problem given to our group is regarding network packet transmission monitoring system. It is formed by a group of computers from Lab A and Lab B, which is Lab A is sources and Lab B will be the destination. So since we are group 6, we are required to implement packet and data transmission involving 6 computers from Lab A and 6 computers from Lab B. We are also required to use a 4-bit synchronous counter and DV flip. So the circuit created must include basic components and connection, basic operation design, and some advanced features. So in our circuit design, the user is allowed to set the maximum number of packet data transfer. So cooperator function is used to make it possible or to monitor the number of packet data being transferred based on the maximum number set by the user. Synchronous 4-bit DV flip-flop up counter is designed. And this image also shows the password design in our circuit. So the decoder function is to use to determine the entered password is correct. So if the uh, password is correct, this tick will light out. And here is the similar fun display is added to the max speed indicator. So if the maximum number of packet data is reached, this would make the light out also. Here we see the schematic for our room, and this for the table for the present state, and here is the answer for the state diagram.
Next, I will presenting on the system implementation. Our system implementation are using marks and demarks for lab A and lab B. For lab A, It consists of X switches that label as computer A1 to computer A8. But in our case, we are using on for our case, it only involves 6 computers. So we have to only turn on 6 switches only. And each of our switches are paired with clock and through AND gates so that the inputs are simultaneously run. In Lab A, the marks only choose one input out of the 6 input from each switches. So the selected input will be based on the 3-bit selector, which is S0, S1, and S2. The selected input will be passed through the single line output that connected to the demarcs in the lab B. So the lab B will receive the output from the lab A and will be passed through a certain computer based on the 3-bit selector, which is S0, S1, and S2. Next, we are using 4-bit synchronous count up counter, which consists of 4 D flip-flops, and each flip-flop stores 1 bit of counter's value. Each of the output will show that the number of packet data that has been transferred will display on the 7-segment display, whereas the Q0 is the least significant bits and Q3 is the most significant bits. Next, we are using clock enabler function. This clock enabler function controls whether the clock signal is passed through to the next stage based on the control or enable signal. The function generates the clock signal only if both inputs are high. So the clock signal is passed through and gate and counter starts to function if only the input start is equal to 1. And then we're also using comparator function, which allow user to define maximum packet data number. In our case, as you can see, we set the maximum limit to 5 bytes. When the counter reach this limit, the LED of the max indicator will be light up. So it shows that it is already reached the maximum number. Next, we are adding advanced feature, which is password for security. So this allows user to set 4-bit passwords, and if the user entered the password correct, the indicator which we are using as LED will light up, will glow up. If the password entered by user are incorrect, then the LED one will not glow up. This will enhance our security of the system.
My name is Adam, and I will present about conclusion and reflection. In conclusion, this digital logic project helped us understand concept from chapter 6 until chapter 8. By working with flip-flops, counters, and combinational logic, we applied what we learned in class to real-world scenarios, making the topics easier to understand. This project also taught us the value of teamwork and communication. During brainstorming and discussions, we combine different ideas into effective solutions. We learn to appreciate each group member's strengths, which help us work more efficiently and achieve our goal. This lesson will help us in future group projects. Finally, there is a room to improve our circuit design. In the future, we plan to upgrade the mux and demux to high-speed models like time division multiplexing (TDM) for better data handling. We also plan to add tools like an alarm system to monitor data loss or signal issues. This improvement will make our design more efficient and advanced. We will continue to our demo part. My name is Adam and I will present a demo for our date circuit. We were given a task which is network packet transmissions. Based on our group requirements, we need to include 6 computers each lab, 4-bit counter, and using the flip-flop. First of all, I will introduce all parts of our circuit. We have lab A and lab B. Here we have lab A and lab B. We also have clock enabler, count up counter, counter comparator, max byte indicator, and password to start. To start the circuit, we need to fulfill all the conditions of the clock enabler, which is connection of lab A and B. Here, the connection of lab A and the connection of the lab B connected with the AND gate and connected to the clock enabler. And we have the second condition, which is the password, and the third condition, the max byte, and the clock is set. We also have one indicator for password and max byte indicator. Here we have max byte indicator. If the count up counter is equal to the max byte indicator will turn on. And here we have password indicator. If the password is correct, the fun indicator will turn on. Firstly, we need to switch on 6 computers for each lab and press clock in lab A to ensure data flow from lab A to lab B. Here we switch on 6 computers from lab A and press the clock to ensure the data flow. And we need to switch on 6 computers from lab B also. We also need to choose data input from 000 to 101 to choose which computer will transfer or receive the packet. Here in lab A, we need to choose either 000 until 101. You can choose only one to transfer the packet to the lab B. As we can see here, we set it as 000, meaning the first computer in lab A will transfer the packet to the first computer in the lab B. The light indicator here shows that the connection between the lab A and lab B is successful. Then we need to press start button and go to password part. Here, as you can see, we have 4-digit password. If the password correct, right here, I set it as 0000. If the password correct, the light indicator will turn on. If the password incorrect, here, if the password incorrect, the light indicator will turn off and the clock enabler cannot function. And for the third one is the counter comparator. We need to set the max byte or max packet that needs to be transferred. For example, I choose 6 and we need to give reset bar and clear bar as 1 to make sure it in the synchronous mode. Here, the output is 0 and the max byte is 6. So the max byte indicator will turn off since the count up counter output is less than the max byte. Here, the clock enabler can function if I press clock, since the first one, the second one, and the third one already passed the condition. If I press clock, the output will increase once. Here, the output will increase. And if I press again, it will change to 2. But the max byte indicator still turn off since the count up counter less than max byte. If I press the clock until 6, the max byte indicator will turn on since the count up counter output is equal to the max byte. If I press more, nothing happened since it will only transfer if the count up counter output is less than max byte. That's all from me.